I hope that I'm audible and my screen is visible to you. The last lecture, we understood how the flow of information takes place from a function file to a script file or from a script file to a function. And how do we put a breakthrough and debug the code? That's what we learned in the last lecture. Today, we will learn how do we solve ordinary differential equations. Before that, I would like to mention or I would like to answer the questions how we can get the ordinary differential equations. So the basic aim of learning Matlab is supposed to be modeling the system. When we modeled any system, let's take a simple example. So we have a water tank in which water is coming using, let's say, tap, or water is going out from the tank. And if we do wanted to know how the height of the water tank changes, how the height of the water tank changes if I increased the inlet flow rate or if I increase the outlet flow rate, how that impacts on the water tank. So how do we do that? So the first, what we will do a mass balance. So rate of income water minus rate of outcoming water is equal to equation. And when we implement the continuity equations, we end up in a differential equations, that is dH by dt, here h is the height, correct, is equal to something. So it's a function of basically input and outputs. So if we modeled any systems and there is a time component in that as an independent variable, then we end up with the differential equations. Even if there might be differential equations where the quantities are going to change with the special variations. Correct? So whenever we try to model any systems, we end up getting a differential equation. If we are model system at the steady state, then the change in that state variables is zero. So dc by dt or dh by dt or dx by dt becomes zero, and that differential equation gets converted into algebraic equations. Now, if we have variations in more than one independent variable, for example, time as well as space. So let's assume that you have a very long rod and you are hitting that rod at one end, correct? As the you are hitting rod at one end, heat is going to transfer from that hotter end to the cooler end, correct? So and as well as, so for example, so let's assume that I have a 10 thermocouples which measures the change in temperature, correct? So if I say that hotter end is at x is equal to 0 and cooler end is at x is equal to 10. So my every thermocouple I placed after a unit of length, maybe meter or kilometer, whatever, or centimeter, correct? So, and if I taken the readings of from those thermocouples, you will find out that the thermocouple at location 1, which is 1 meter from hotter end, gives you some temperatures. Then thermocouple at a location 2, which is 2 meters from your hotter end, gives some other temperature. So and so forth. Temperature is decreasing toward the cooler end. So now if you assume that this is my special variation. So temperature 1, 2, 3, 4 thermocouples is having a different value. So there is a special variation. Now, if you're going to take temperatures at time t is equal to 1 second, time t is equal to 5 seconds, after every 5 seconds you are taking the readings. You will also observe that the thermocouple at location 1 shows me different readings at a different time interval. So there is a variations along the space because thermocouple 1, 2, 3, 4, so and so forth have shown different values of temperatures at a particular time instance. So there is a spatial variation. Now, if you again observe data, you will see that thermocouple 1 shows different temperature values at a different time interval. So for instance, 1 second it shows some values, 5 seconds it shows some value, 10 seconds it shows some value, 15 seconds it shows another value. So thermocouple 1. So there is a variations in the time also, the variation with time also. And hence, if I try to model this type of system, I will end up with partial differential equation. So I think, am I clear? When we end up getting differential equations, when we end up getting partial differential equations, and when we end up getting algebraic equations. Now, when we try to model a system where there are a lot of complex dynamics occurring simultaneously, there might a chance that we can get the combinations of ordinary differential equations, partial differential equation, algebraic equation. And when we try to simulate the system, or when we say that I am going to simulate the system, I need to know the ways to solve these ordinary differential equations, partial differential equations, and algebraic equations simultaneously. Helps you in providing the solution of all these types of equations. Today, we will, and in subsequent lectures, we will going to see how we can solve or simulate ordinary differential equations. So here on the screen, you will see that there is an example from electrical engineering. So it has a resistance and it has a voltage source. And if I wanted to find out the change in current, I can get this type of differential equations. It's a domain specific. You should have domain knowledge to understand how these equations comes. But this is the way these equations we can write. We know the second example is Newton's cooling law. This is what is the Newton cooling law. We learn the Newton's cooling law. So theta indicated by the temperature here, K is a constant, and theta S is a steady state. So d theta by dt is equal to minus K theta minus theta S. So Newton's cooling law. There is a classical example from mechanical engineering, that mass and dampers. So if I going to write a fundamental equations for displacement of the mass, I end up with second order differential equations like this. This is again classical example from chemical engineering, where I wanted to see how the content temperature is going to change if I had a heat flow to the jar. So this is what is the equations. So all these equations can be written by using the fundamental laws or the basic knowledge of that particular streams. However, when we wrote the equations, that's what is called as modeling the systems. And now we started with the simulating the system when we try to solve these differential equations. So how do we solve these differential equations? We will see. Now, Matlab has the syntax for solutions of this ordered differential equations. Uh, Before that, going to the syntax, let me explain you how do we solve differential equation by using pen and paper. You might have gone through this. So, for example, if I have a dx by dt, correct? So, I wanted to solve dx by dt. We can discretize it. So, when we discretize it, we have x at the instant 1 and we wanted to find out x value at the instant of 2. So dx by dt can be written as x of 2 minus x of 1 divided by delta t. That's a dt which is in downsides when we write dx by dt is a delta t. So we know that time interval or sampling times, correct? And whenever we solve order differential equations, we in general solve IVP, that's the initial value problems. Is IVP, so we know the initial value. So we know at a time t is equal to 0, what's the value of my state variables. So in this case, x of 2 minus x of 1 divided by delta t. So we know x of 1, we know delta t. So we can transfer this on the right hand side and we should know everything on right hand side. Then we can calculate x of 2. Once we get the x of 2, we can calculate x of 3 because you know x of 2. Now we can write dx by dt as x of 2 minus x of 3 minus x of 2 divided by delta t. Correct? So in this way, we can march in time and solve the differential equations, get the state variables. Correct? So this method is called discretization. There are n numbers of methods like Garanga-Gupta methods. RK4, you might have learned RK4. Trapezoid methods. There are so many numerical methods available for solution of ordinary differential equation numerically. Correct. So what Matlab did, all these methods, Matlab coded for all the problems and generalized it. So all that code, which basically simulates these methods like RK4 or trapezoids or whatever maybe that there are other methods. Correct. So those method has been coded by MATLAB, written in a functions, and that function is in a general is called as a solver. Solver is a common name for any language. So solver basically is the code which has been written based on the logic given by, let's say, Newton-Raphson's or Runge-Kutta methods or discretization methods, so and so forth. Correct? So we need the solver to solve these differential equations. So what are the solvers available in MATLAB? There are a lot of solvers available in MATLAB. That is ODE 45, ODE 23, ODE 113, ODE 15S, ODE 23S, ODE 23T, and ODE 23TB. There might be more. Correct. So ODE 45 is based on RK 45. Rangakutta 45. So all these methods are based on some or the other algorithms or methods proposed in the literature. So these solvers are readily available at your disposal. Then what is the syntax? The syntax is written here. I would like your focus on this syntax. So this is solvers. We know the solvers. Then at the rate of function file name. So whatever will be differential equations which we are going to solve, we need to write in the function file. So that function file name has to provide here. Okay. Then there's a time span because when we solve the differential equation like dx by dt, we know x of 0 and we know up to what time instant I wanted to solve this. For example, if I wanted to solve it for 10 times, 10 minutes, correct? And I say that at every minute I am going to take my outputs or measurements. So delta t becomes 1 minute. So if I wanted to discretize this, I have x2 minus x1 divided by delta t. So I can get x2 which is correspond to the second minutes, x3 correspond to third minute, x4 corresponding to fourth minute, so and so forth. I will mark in the time up to 10 minutes. So depends on the ODE, depends on our applications. We wanted to know how much time we wanted to march. So that is what is the time span. So this is second slot is for time span. Please do not interchange this. Second slot is for time span. The first slot is for function file name is for time span, and third is for initial conditions. We know that for solution of one ordinary differential equation, that's IVP, we need one initial conditions. Like in this case, dx by dt, if I discretize this x2 minus x1 divided by delta t, I should know x1 value. Correct? So that's my initial conditions. So if you provided all these informations, MATLAB solves it using the solver that is ODE45, ODE23, whatever may be that, gives you output in this fashion. The first argument of output is the timestamp at which these output MATLAB is spitting. Okay, so basically provides you column vector, one column, many rows, in which there is a lot of time instance provided and why. Correct. So these informations MATLAB will splits. So as I explained, time span, a range of independent variable for which we want to solve the differential equation. An initial condition, value of the dependent variable at the independent variable equal to 0. So this is the syntax. Now, how the flow of information takes place. As I mentioned, we need to write a function file. Function file, we wrote a lot of function files. In function file, there are input argument is required. Here, basically, we need to provide two input argument. One is the time, and another is the y. So that input argument, it automatically takes from the MATLAB syntax. Once you provided the time span and initial condition, it automatically takes. But the fashion in which you are going to write should not be interchanged. The first is independent variable, second is dependent variable. Should be very clear. Should be very clear. And here you will write all your differential equation and subsequent files. This function files or this syntax which I mentioned just now, this is you write in the script file. So once script file sequentially runs, hits where you wrote this syntax, then it's understand that I need to solve the ODE because we asked ODE solver. That's ODE 45 or ODE 23s. As soon as that number names MATLAB finds out, it understands that need to solve the order differential equations with the file name given, with the time span and initial condition. It takes that all data, and goes into the function file. Substitute the data which it brought from the two slots of the syntax, substitutes here, and then whenever this data is required in the downsides, it puts that data and solves, and then come back again to the solvers. Okay, and solver try to solve it until it ends the time span. So this is way the information is expressed. Now I'm going to solve a very simple example like dv by dt is equal to 4. Please look how I am going to solve it. In between, I'm going to wait here for 2 minutes so MATLAB is going to start, as well as if you have any doubt, please do ask me. Okay. Let me show you how to simulate. The first important thing for this is you should change the directory to your local folder which we created. So I am going to change to the class 21. Okay. And then I am going to write first the script file. So here I am going to open one script file, CLC, clear all. And then I have I have now differential equations as dv by dt equal to 4. So this is what the differential equation I'm going to solve. This is dv by dt is equal to 4. That's what the differential equations. So I have initial condition of v0. Let's assume v0 is equal to zero point 0.5. So this is initial condition given to me. Correct. Let's assume that we wanted to solve it for 10 seconds. So my time span equal to starting from 0 to 10. Correct? This is my time span. Initial condition I have given. Then I can go and look at the syntax. Syntax is t comma y. You can write any variables. Is equal to, let's have solver OD45. This is what my solver. At the rate of, I mean, in newer files you don't need at the rate of at the rate of function files. So ODE example 1 as a function file name. Correct? And then time span. So it's initial condition, time span, and then initial condition as v0. So this is what completely I wrote. So I saved it, let's say, main file for OD1. I given the name. This is what we know. Now we are going to go and create the function file here. Same as first word is functions. My outputs, we need to outputs. Yeah. So the output here I can say dvdt is equal to name of the function file which I said odexp1. So it's a odexp1 and input argument. The first is dv by dt. So t is my independent variable and let's say v is my dependent variable. This is what I wrote. And then dv dt is equal to 4. This is what my differential equations. And if even if you did not wrote n, that's fine. Okay, and save. Now you will see that dv dt output is I am giving. I am not using t and v because in my differential equations right hand side it's constants. That's why these arguments which has been supplied is not useful at this point of time. Correct? I am going to save it and I am going to now run it. I'm expecting t as a column vectors and y as a column vectors. So if you open this, you will see that t starting from 0 which has given a t span and 10. So if you go, last value is 10. And this is what is my output, dv by dt's outputs. 0.5, initial value is 0.5 and then it's increasing. Clear? Now let's go and check the flow of informations. So let's put the breakthrough here. So I have a breakthrough. I'm running it. So I'm going step Now V0 value, if you look at this V0 value, it's already Matlab knows V0 value is zero point 0.5. Let's look at the T-span. T-span value is 0 to 10. That's Matlab knows. Now it comes here. So if I click the step in, it first goes in OD 455. I don't want to go there. So what I will do, I will go in my function files and put a breakthrough here. Now I will come to the main files, and at this point of time, we really know time span and V0. So these two values it will take with him and goes. Uh, it goes there. Okay. So now if you come here and look at the t value, so it taken the t is equal to 0, the first value of time span, and v is equal to zero point 0.5. It calculates dv by dt, which is right now 4. dv dt is 4. And once you continue, now you will see that t value is 0.05 and v value has been changed to 0.521. So it solves the dv/dt between 0 to 0.005. Correct? So if you discretize it, if you wanted to solve it using discretizations, the delta t is 0.05. So 4 multiplied by 0.05, okay, plus initial condition, that's zero point 0.5, is what it has been telling us the value of V2. So if you continue again, its value of V is changed and value of T is changed. Are you understanding how it's marching in the time frame? So it will do until it reaches time is equal to 10 seconds. In this way, it's try to solve the ordinary differential equations. If I had 4 into V, for examples, the results might be something different. So now it's 145. Look at the values of Y. 0.5, 5258, 5528, 5813. So these values has been changed as compared to earlier. So this is the way we can solve ordinary differential equation of first order. Does anyone have any doubts on this? It's extremely important. You should understand the flow of information, how it is taking place, and this syntax. That's too important. And how do I wrote the differential equations in the ODE file? I was having ODE dv by dt is equal to 4. The left hand side dv by dt I wrote as a one single variable dv dt is equal to what, and maybe on the right hand side I just wrote here. Any doubts, any questions on this one? Can you people try to solve this? The function is ds by dt is equal to 3 into sine t. This is what is the function. The OD ds by dt is equal to 3 into sine t. And here initial conditions for ds by dt or s of 0 is basically 3. Can you try to solve these functions and show me the OD solutions. Don't plot it. If someone knows plotting, then they can plot. If not, doesn't matter. After this, I'm going to take the plotting exercise. So the function there is ds by dt, or the OD is ds by dt is equal to 3 sine of t. This is my OD, and s of 0 is equal to 3. So write the main file as it is. Here it is given, and then function file is like this. Who is going to share his or her screen? Is anyone wanted to share screen?
Sir, I'll share my screen, sir. So should I?
One thing I wanted to mention here. See, if you are not going to respond, like, or if you are not going to show your screens, I assume that you understood, correct? And I am not going to blast on you. I am not going to pester you. It's a very straightforward give and take policy. My job is to explain the things the way I can, Your job is to grasp. There is no such a feedback mechanism where I know that you understood things or not. If you are not going to speak, I assume that you understood what I'm going to say or what I already told you, and I can go ahead on the next topics. Within a stipulated time frame of the semesters, the responsibility rested on my shoulder is to complete the task. And how I taught, my salary is not going to deduct, and no one is going to tell me anything. Only thing you can screw up me in a feedback, which is of no use. Correct? So, if you people decided that you are not going to respond, I will go ahead and straightforward teach what I wanted to teach. Yeah. So I hope that you solve those differential equation. Now here is another examples of another equations where the differential equation is, oh, you can, yeah, let's solve this differential equations. So dy by dt is equal to, and we can, you know that dy by dt can be written as y dash or a dash. So y dash of t is basically can be written as dy by dt. The equation is alpha y of t, alpha y of t minus gamma y of t square. Whereas alpha's value is 5, gamma's value is 10. And this is one differential equation of first order. We need one IVP. Thus y of 0 is 10. Y of 0 is 10. Can you solve this? Write the script file, function files, and try to solve this.
Hello, sir. Sir, the time span in this case would be
Yeah, anyone wanted to share their screen for this problem?
Sir, I will share my screen, sir.
Hmm. That's fine. Okay, thanks. Okay, so I'm going to stop here. We will meet in the next week. For that, I wanted to cover the plotting things before your midterm. So that we will finish in the next week.